Hello everyone and welcome to my talk. My name is Dörr and I have the pleasure to talk to you about some asymmetric cross-covariance. This is joint work with Niklas Hansen and Martin Schlatt. Let me start with a brief motivation. There's a great interest in making good predictions for different quantities in various branches. For example, we can think of the amount of raw materials in certain locations. As there are usually dependencies between the variable of interest and other ones, it is natural to include this additional information, namely the cross-covariances, in our predictions. Therefore, the focus turns to the construction of valid multivariate covariance models, and in particular to asymmetric ones, as asymmetric dependent structures are often observed in practice. Getting formal now, we denote Z as zero mean, second order, M-variate, real-valued random field on RD. The domain of the field can be interpreted as purely spatial locations, but we can also interpret one dimension as a temporal domain. The cross-covariance of Z is then a matrix-valued function with the respective covariances between the process's components as entries. If a cross-covariance function is translation invariant, we call it stationary. If it can be even represented by radial functions, we call it isotropic. For notational convenience, I will simply write C of h, with h standing for the lag vector x minus y in those cases. From a theoretical standpoint, the problem of characterizing cross-covariance functions is solved for stationary and continuous ones, as we have this multivariate version of Hoffman's theorem saying that every stationary and continuous cross-covariance function is the Fourier transform with regard to some matrix-valued measure on Rd, which forms a non-negative definite matrix when evaluated at Born sets B. However, we do not know these Fourier transforms except for some special cases. Therefore, we have to take a step back and develop some, say, rather constructed or physically motivated approaches which lead to valid cross-covariance functions. Several approaches have been proposed in the literature, but some are limited to the construction of symmetric cross-covariance functions. It is immediate from the definition that we have this relation here, but in general, the symmetry condition doesn't hold. In practice, the main source of asymmetry stems from some kind of shifts, especially in the temporal domain. This is the idea behind the so-called type 1 asymmetry. Here, we do not focus on a temporal domain, but simply say that a stationary cross-covariance function is symmetric up to shifts if it can be represented by a symmetric functions with the argument shifted by some vector. Analogously, we call the cross-covariance functions isotropic up to shifts, with the respective symmetric functions even being radial. The prototype fitting to this definition and one of the earliest asymmetric models is the so-called delay model, which can be constructed as shown here. We take a random field y with stationary covariance function and construct a bivariate field by taking y as the first component and y shifted by a fixed vector s as the second one. We now generalize this model, and instead of a fixed shift, we replace it by random ones. So if we have n independent, continuously distributed random vectors and a univariate random field with some stationary covariance function, we can construct an n-variate random field by taking the univariate random field and shift it by the respective random vector. The resulting cross-covariance function then looks like this, provided that the integrals exist. This resembles the so-called kernel convolution method on secondary diagonals, although the construction mechanisms and the underlying assumptions are different. We can, of course, include some scaling factors and some error terms here, but for our purposes here, it is sufficient to look at this construction. Recalling what we have already discussed so far, we focus on two questions. First, what kind of asymmetries can we produce with that model? And second, can we get explicit forms for it? Starting with the first question, we can show that the properties of the random shifts determine the symmetric properties of the cross-covariance function. In fact, symmetric shifts lead to a symmetric cross-covariance function, and in case that the underlying univariate covariance is isotropic and the shifts are even radially symmetric, we get an isotropic cross-covariance function. Analogous results hold up to shifts. So if we want to break out of this class of asymmetry, we have to choose asymmetric random vectors as well. But before we do that, we first assume the shifts to be multivariate normal ones and thus stay in the class of asymmetric models up to shifts. We then get the following proposition here, which allows for a nice interpretation of the resulting cross-covariance. So if we have an isotropic univariate covariance function that is valid in all dimensions, and if we have some vectors and positive definite matrices, we get a valid cross-covariance model where on the secondary diagonals we have the joint possibility of shifting, rotating, and rescaling with the respective matrices for rotation and scaling stemming from eigendecomposition with regard to the given positive definite matrices. Let us now turn our attention to the bivariate case. Without loss of generality, we can take the first shift to be 0, so that we have to solve integrals of this form here. As a nice feature, we have this result, which gives an equivalent representation of our cross-covariance function in the trivariate case. What makes this representation interesting is that it involves sums of the respective shifts instead of differences as in the original formulation. Therefore, if we can solve the integral in the bivariate case for a shift whose distribution is closed under summation, we immediately get a valid trivariate expansion as well. Considering the case of valid cross-covariance functions on the real line, the first distribution which comes to mind being asymmetric and closed under summation is the gamma distribution. Based on the gamma distribution, we can actually get quite a lot of explicit forms for different underlying univariate models. To give you an example, if we take the Gaussian covariance function and the gamma distributed shift, we get this function here on the secondary diagonal, which is a product of an exponential and a parabolic cylinder function. For some special cases, this function simplifies just like here for the shape parameter p being 1, where it reduces to a product of an exponential and the survival function of the Gaussian distribution. Here you can see a plot of this model on the plane. As in the special case of the Gaussian covariance, the resulting integral factorizes such that we can generate valid models for any dimension d by considering the one-dimensional case and using independent random variables as shift components. The asymmetry is evident. For example, here we have the correlation decreasing much slower to the left than to the right. For some special cases, the Cauchy model also allows for a variety of different cross-covariance functions. For example, taking the parameter of the Cauchy model to be 1 and the density of the shift to be a cutoff quadratic monomial, we get this cross-covariance function. If we plot this function, we see that it exhibits a very interesting behavior as the curve significantly changes for varying parameter r and fixed b, but we could see the same effect vice versa, just in the opposite direction. We can see that the curve transforms from an unimodel into bimodal ones, and that the locations and heights of the peaks change for different values of a. Also, we can see here the case of a symmetric model for a equals -4. So the bottom line from this example is that we can capture very different asymmetric dependent structures on the secondary diagonal with just these two additional parameters a and b. That brings me to the end of my presentation. Thank you all for watching and have a nice rest of your day.